For 73 years, the wreck of the RMS Titanic sat completely hidden on the floor of the North Atlantic. The failure to find the most famous shipwreck in history came down to a specific technological bottleneck rather than a lack of effort. At 3,800 meters, the ocean is pitch black, freezing, and exerts a crushing pressure of 5,500 psi. Scientists tried using sonar, but returning acoustic waves cannot distinguish between a ship's steel hull and a jagged rock formation. The ocean was simply too vast, and the environment too hostile, to map using sound alone. Exploring the depths required an entirely new methodology. The early alternative to sound waves was encasing human beings in heavily armored, localized submersibles, like the Trieste, and sending them down to physically look around. But using manned submersibles like the Alvin for large-scale searches presented severe operational flaws. Life support drained heavy batteries, leaving very short bottom times. And to withstand the pressure, pilots had to peer through tiny acrylic viewports, illuminating only a small patch of the seabed. A lost ship leaves a search area covering thousands of square kilometers. Scanning that expanse by peering through a 6-inch window for a few hours at a time was mathematically nearly impossible. Putting human bodies at the bottom of the ocean inherently limited exploration. The requirements for human survival drastically reduced the actual time spent searching. In 1985, an American and French research team led by Dr. Robert Ballard approached the problem differently. They realized that looking for a single, intact ship in the vastness of the Atlantic was the wrong approach. This illustrates Ballard's strategy. When a massive vessel sinks, it scatters thousands of items. Instead of hunting the ship, they searched for its 3-mile-long debris field. But standard sonar sweeps right over small, scattered objects buried in the mud. To find the trail, Ballard's team needed a tool that did not yet exist, a system that could continuously and visually scan the ocean floor without the life support limits of a crewed submarine. The solution was the Argo system. Argo was not a manned submarine. It was a revolutionary, uncrewed, deep-sea camera sled built to serve as a permanent eye in the dark. This diagram shows Argo's sensory apparatus. Stripped of a pressurized crew cabin, the sled was packed with high-resolution cameras and powerful strobe lights, engineered to pierce the total darkness over a wide swath of the seabed. Connected by a long towing cable, the surface ship could pull the sled just a few meters above the seafloor, covering vast distances non-stop, day and night. Crucially, Argo featured real-time image transmission. Scientists could sit safely in a surface control room and watch a live, continuous feed of the abyss as the sled scanned the mud below. By removing the human body from the deep ocean, Argo multiplied our ability to observe it. On September 1, 1985, the crew sat in the control room monitoring the live Argo feeds. For weeks, they had seen only empty mud. Then the cameras captured an unnatural shape. A massive steel boiler appeared, followed quickly by scattered luggage and pieces of coal. By following that trail of debris, the cameras finally traced a path directly to the upright, rusted bow of the Titanic. This discovery verified that high-end optical technology, not sound waves or manned spheres, provided the visibility needed to explore the abyss. While finding the Titanic made global headlines, the scientific community was reacting to a different revelation. The success of Argo proved that traditional manned exploration was rapidly becoming obsolete. The efficiency of an uncrewed, tethered sled directly accelerated global funding and development for modern remotely operated vehicles, or ROVs. Modern ROVs took the foundation Argo laid, real-time video and tethered power, and added multi-directional thrusters for maneuverability, robotic arms, and complex scientific sampling tools. The Titanic expedition changed how we approach the deep, transferring the heavy physical risks of exploration from human divers to highly capable, expendable robots. Today, ROVs are used to safely map volatile environments that would be catastrophic for a manned submarine to navigate, such as active deep-sea volcanoes and boiling hydrothermal vents. This constant monitoring allows marine biologists to collect samples and study alien ecosystems that thrive in the crushing depths without a single drop of sunlight. The imaging technology developed for the 1985 expedition gave humanity permanent, unblinking eyes in the most hostile frontier on Earth.